Thank you, Ingrid, for the sweet introduction. So, Wolf and I will give you a talk about neotropical palm communities, and I'll give some general information in the beginning, and then Wolf will take over and present the more analytical part of the data. So we saw some numbers from Jean-Christophe earlier, which covered South America, so these numbers are slightly different, but see that the neotropical palm diversity is substantial, and again the same division between subfamilies as we have worldwide. Also, palms have a lot of different growth forms, as you can see here. And that means that they can occupy many different parts of the ecosystem, from the ground level to the canopy level, and also the climbing palms, of course, as we saw a lot of in Thomas's presentation. And another very obvious difference when you do fieldwork with palms is that they can be cespitous or solitary, and that represents different reproductive strategies, which may be quite important for the composition of the communities. So this vegetation map shows the major vegetation maps, and what we will show you today is based on a sample of the palm communities that we have done over the past several years in the palms project that many of you have participated in. And for this particular purpose of the palm communities, we made samples in the 4 countries which were involved in the project, from Colombia, Ecuador, Peru to Bolivia, and also we have done some sampling on the Yucatan Peninsula in Mexico, and some sampling in the Amazonas of Brazil. So we worked with this transect method, which was also presented before earlier today. This was the kind of data we took in subunits of 5 by 5 meters along a 500-meter transect. So we identified and counted all the individuals and classified them in growth sizes, from adults to seedlings. We took soil samples also, slope and other features of the habitat. So over these years that the project lasted, we made 550 transect and counted some half million individuals in 109 species. So obviously the whole palm flora is not represented in these transects, but that's maybe not surprising. Most of our transects are in tropical rainforest, and as you all know, that's not homogeneous kind of vegetation. And the major divisions of the rainforest, you can see here the terra firma, which is the never flooded areas, and then we have the floodplains, and sometimes we have also permanent swamps, which are always wet, and in some areas we have the white sands coming up, and all these have different palm communities. Here's some examples of the terra firma. This is a picture from Chapare in Bolivia, with tall rainforest, and again with our Iriaceae del Quindío, which is so common all over, and this is from Bolivia again, and it's also a dominant palm in the tall rainforest there. Here, Retina and Neonoma in the understory. But even on the Tertiary we find that there's a lot of division in different habitats, and around Iquitos that's very much associated to different soil types, and that's the case all over. But in Iquitos we were lucky to have a map of the soil mosaic here, and you can see the Amazon River here, and so this would be Iquitos right here, no, right here, and these blue areas here are soils which are derived from the Pebas formation, which we have heard about a few times also already, with the marine intrusion that came over the western part of the Amazon and deposited marine layers which can be recognized from the fossil fauna in them, so they're quite well described. But then after the Pebas formation, there were other non-marine deposits, and so this would be the Nauta formations, which are younger soils, and along the river here we have some old previous floodplains which are not flooded anymore, but they still have the structure of quaternary terraces. Then, of course, there's the inundated areas over here with more floodplain forests, and some of them here are derived from it's called the Pastaza farm, and they're derived from volcanic soils in the Andes of Ecuador mostly, and the pink ones are more recent floodplain soils. So this is interesting to see how different the communities are in a forest that looks very similar on the surface. So these red dots are some of our 550 transector which were made in the environment of Iquitos. And we can see here that they're quite rich communities with up to 30 species in a transect of so it's a quarter of a hectare, and here for 9 or between 6 and 9 transect we have species richness of 43 to almost or to 56 species. So very, very rich communities, and when you go there you are amazed. In sometimes you could find in just one farmland you could find 10 different palm species just growing together. But we can also see here, which is the purpose of this slide, to show that even if these different soil types, they share a lot of species, there's also some dividing out here. And even there's a little contingent of species here which are special for each of the soil types, and others here which are shared by some of them but not present in all of them. So these communities, even if they are very rich, they also have some specialization of species to each of the different soil types. The floodplain forests, they are more homogeneous, and they were doing from our experiences that they would have a very similar flora. The palm species on the floodplains are widespread, and we find the same species over large distances in the area. Then the white sand, the forest there is quite different to walking. If you look here, it's dominated by rather narrow, thin stem, very straight stem, not branching, and not very big trees, and it's called Varial there, and quite a different tree flora also, and the palm flora of the Iceland is quite poor also, but it has some spectacular examples, one of which is this, it looks like Mauritia flexosa, but it's actually Mauritia cana, and you can tell it from the flexosa by this bunch of fibers which accumulate among the leaves under the ground. Here's the true Mauritia, and that's the dominant in the swamps, which are wet all through the year. They don't depend on the flooding pulse of the river, and Mauritia, of course, is the dominant palm there, together with a few other species, and the adaptations, for instance, of the pneumatophores is very particular, and shows or demonstrates this ever-wet habitat for these. So those are the Mauritius ones, which were quite extensive around Iquitos, but also found all over the Amazon forest. The mountain up along the slopes, I think it was Jean-Christophe who showed a slide of how the declining species along the elevation slopes, and this is just one picture from Bolivia, where we have this gradient from the lowlands up to the highlands here, several thousand meters, and if we had made transects all along the slopes, we could have seen the same decline in species from the lowlands here up to the higher areas. But if we just want to make it simple and look at the lower montane forest, we can see that we have many species which are, some of them shared with the lowlands. This Leucapus bacava, of course, is very abundant in the lowlands also, but then we have the lower montane forests such as Tregear and Ifanus horrida, which also does go out into the lowlands, but it's mostly associated with this lower mountain. And then the Astrocardium, I put Gratum on, I have to check with Jean-Christophe to see if it's the right one, but it's from Bolivia, so it should be Gratum, I think, but we can check it later. And then when we go up to around 1500, 1700 meters, we get a much poorer forest with, in terms of species, but sometimes very high abundances. And this is just one example of the very abundant occurrence of Dictyocarium around those elevations. But we also find very dense populations of Leucapus bacava all the way up to these elevations. And then several understory species also of Euterpe and Geolomas and Camedores, etc. To the north and the south of the rainforest we find the dry forest, and this is an example on the southern side. So this is the seasonally dry forest from Bolivia, where we find poor palm communities with maybe 5 or 6 species like this Bactris here. And on the dry side up in Mexico, we find similar forest, also deciduous forest, but when you walk into it, it looks quite completely different from the dry forest in the south, because they are dominated by the coryphoid palms with palmate leaves. So you have a completely different feeling, that it looks like a completely different forest. And now we know, of course, that the coryphoids are boreotropical, and they dominate the northern dry forest, but have only recently come into the South American continent. But it's visible just from a first view when you go and make transects in these forests. Very few species, maybe 4 or 5 species apart from these Strivax. There's also a couple of Camellorias and some Sabal species, 2 species of Sabal. Then of course some more extreme habitats which are influenced by flooding, and one of them is this example of on the Yucatan Peninsula also of these very low-lying areas which are flooded by salt water, and this species of Accelerate, it forms a monotypic stance there. So we go down to communities with just a single species in these extreme dry areas. If we look at the diversity between the different habitats, we see that the terra firma forest, as I suggested, was the richest. Well, this is species per transect, average 25 in the wet forest, and the floodplains much lower, and the swamp forest even lower in terms of species richness. White sand also poor, but a little bit richer than the swamp forest. Deciduous forest low. The low mountain forest relatively high, maybe 20 species, and upper mountain forest again dropping down to the average of 10 species. So these habitats are quite different in terms of the diversity. And the composition of them, also that's another thing which is very obvious when you walk into these forests, is to see how many cespitous species you find. And again here, the white has the highest number or percentage of cespitous. Of course, the total number was not so high, so it's not absolute numbers of diversity. Otherwise, the proportion of cespitous species is fairly similar in these tropical rainforests over here, and then they are lower in the untamed forest and the deciduous forest. So we have speculated about that, but there's no obvious answer to that as far as I'm concerned. Here's another difference that I mentioned, the difference between coryphoid palm dominating the northern forest and the pinnate leaf. You can see here, this is not come out a little bit better, but the gray scales here are the proportion of pinnate leaf, and the black scales are the proportion of palmate leaf. So that's a graphic illustration of these different kinds of palm forest, which has this historical explanation that Jean-Christophe also talked about. And the regional differences also here. If we take the Amazon part here, we have the transects located all the way from the far north of the equator. The equatorial line is here down to Bolivia, and these two far away places, they have much lower species accumulation curves, whereas the highest number is in the Iquitos area, just near the equator. So we have a very strong latitudinal gradient of species richness along the western Amazon. So that was a little description, and then Wolf now will talk about the drivers of these patterns that we see.
Thanks, Henrik. Hello, everybody. This morning, Jean-Christophe gave an excellent introduction to the evolutionary dynamics underlying South American palm diversity. And in my talk, I would like to put my geographical ecologist hat on and talk a little bit more about palm diversity patterns across the neotropics and the underlying environmental factors. When I was asked to give this talk, I realized that I personally haven't been working on neotropical palms for the last 4 years. So what I'm going to present here may be old news for many of you, but somebody told me that's what keynotes are all about, so let's just give it a go. If you want to analyze the kind of patterns that Henrik just described, it's necessary to break them down into tractable descriptors of biodiversity that can be related to predictors. And there are many of those, including the number of species in the community, species richness, the identity of the species in the different communities, but also whether the species that co-occur in a community are close or distant relatives, phylogenetically speaking, from which part of the palm phylogeny they come, phylogenetic composition of the community, and also how many phenotypes there are in the community. This is often referred to as functional diversity, although I would more generally call it morpho diversity, because we often don't have a very clear idea about the functional relevance of the things that we're actually looking at, and also which phenotypes there are in terms of the functional morphological composition of the communities. And beyond those measures, eventually we all strive to understand the functional implications of this and what is driving interactions and ecosystem functions and services and so on. But I'm not going to go into that because we're frankly not very far on that front. So the kind of studies that I will talk about here today basically all take the same approach, namely relating this kind of descriptors of biodiversity statistically to some potential driving forces, including climate, soil properties, hydrology, topography, light availability, canopy conditions, biotic interactions, and dispersal. And we've already heard much about many of those factors in previous talks on this conference. In 2011, we published a global review where we looked for studies that have taken this kind of approach and try to find evidence for an influence of those drivers on palm species distributions, palm community composition, and palm diversity across a wide range of different scales. After Luke's talk earlier today, I don't really need to explain why it's really important to look at different spatial scales. For this specific review, we used a terminology that referred to local scales for extents of the whole study up to a kilometer, landscape scales between 1 and 200 kilometers, regional scales up to 2,000 kilometers in extent being the maximum distance between any two places looked at in the study, and everything larger than that, continental or global. And you can see that there is quite mixed evidence for the influence of those different things on different aspects of palm diversity, with, for example, climate appearing to be quite dominant in large scales and so on. But there are also a lot of gaps in here. And one interesting point about this is that when we did this review, it was really striking to see how much of this evidence actually comes from the neotropics. It is a global review, but I haven't calculated it. I would say 80–90% of this comes actually from the neotropics. So this is the part of the world where this kind of study has been conducted most actively. So what I would like to do now is I would just like to go briefly over continental scale patterns of palm diversity in the neotropics and their drivers as they have been inferred from macroecological studies. And then after that, talk a little bit about regional scale drivers, just highlighting some specific studies, and then I'll have a little bit of outlook on where we might be going with this kind of approach in the future. So you've probably all seen this map in one or the other version. This just shows the number of palm species across the neotropics. There is strong variation, and if you plot it against latitude, you see a very beautiful, very classical latitudinal gradient with the maximum, with a peak of species diversity at the equator. This has been studied macroecological by the Ecoinformatics and Biodiversity group in Aarhus, and there are interesting there are two aspects to this pattern basically. One aspect is the overall range limit of the palms. This is I mentioned this under the species richness gradient because it's a very important difference between zero richness and some non-zero, some positive richness. And then there is the pattern within the distribution of palms. And interestingly, a study by Daniel Kissling and collaborators from 2012 found that the range limits of palms globally and also in the neotropics are very strongly determined by temperature. Well, it's maybe not that surprising. We've always known that in a way, but it has been shown statistically. It's getting more interesting if you compare this to the determinants of palm species richness within the range, because there temperature doesn't show up as a very important thing, but the gradient seems to be determined mainly by water availability and secondarily soil. So there seems to be a shift of importance from energy variables at the extreme latitudes of palm diversity in the neotropics to water variables towards the center of this gradient. And this is something that has been hypothesized as a macroecological hypothesis, that namely that there is a shift between water and energy importance with latitude. And we've looked at this in more detail in a study that we published in 2011, where we looked at using a sort of moving window approach, looking at correlates of palm species richness from the equator to the poles. I think this must be the northern hemisphere, and this is the southern hemisphere. So as you go from the center to the edges, you go from low to high latitudes, and the y-axis is the strength of the correlation between palm species richness and water and energy variables. And you can see the importance of energy increases, maybe not very strongly, but clearly significantly from the equator to the poles, and water is doing the opposite thing, mirroring this observation that the range limits are set by energy, whereas the gradient itself is more driven by water. So those are basically correlations, and as we all know, we can't infer causation from correlation. There has been an attempt to get a more mechanistic understanding, asking what is actually driving this relationship between warm and humid climates and high palm diversity. Pretty correlation there, suggesting that the high palm diversity in those warm and humid climates is actually driven by a higher rate of diversification in those climates. It's still not fully mechanistic, but it's providing us some indication of what might be going on here. Maybe. There are other interesting observations about palm diversity across the neotropics. This one was shown in 2006, just breaking up the palms into the 4 subfamilies that are naturally occurring in the New World. And this is interesting because the 4 subfamilies show very different patterns. Ericoids, which, as both Henrik and Jean-Christophe show, contribute the bulk of neotropical palm diversity, show a pattern that is rather similar to the overall pattern. But ceroxyloids are doing something really different. So are coryphoids. and color modes with admittedly rather few species. They have, again, a very different pattern. So this might suggest that, well, how appropriate is it actually to analyze palms as one big unit if those different clades are doing different things? And the interpretation of the study was that there were historical legacies that, independently of whatever mechanistic link is going on between climate and species richness, sort of give another imprint on species richness patterns. For example, coryphoid palms having northern origin, thus being more diverse in the northern part of the Neotropics. Well, maybe that might not be true. Angela's talk on the first day of the conference suggests otherwise, but it's an idea, and we definitely need to look more into that. This really illustrates that it is sort of dangerous just to take species level data, throw them on a map, and look at correlations, because those species are connected by phylogeny, and they have evolved, and it's necessary to take those phylogenetic relationships into account if you really want to understand how those gradings are generated. That's not an easy thing to do. We have made some steps into that direction. One way of doing it is looking at measures of phylogenetic structure and composition of assemblages. And this is one thing we did, in this case, for really broad-scale assemblages in approximately country-size units across the Neotropics, not country-size for Brazil, but for most of the other parts of the Neotropics. And this basically shows how closely or distantly related the palm species in those units are, with red and big blobs indicating close relatives and blue blobs indicating distant relatives. And you can see that if you look across the Neotropics, there is a strong signal of phylogenetic clustering. So things that palms that occur in the same areas tend to be close relatives. That can be for several reasons. That can be because of biogeographic dispersal limitations. So it basically just indicates that you have different clades that are centered on different parts of the Neotropics and have evolved in different parts of the Neotropics. And we really wanted to know why that is. And one thing we did in this study, which by the way was, oh, I forgot to put the reference, it's the Kissling et al. Study 2012 in PNAS. One thing, oh, there it is. One thing we did is that we scaled the extent of the study to see what happens if we look at the relatedness compared to different reference. And so if when we decreased the scale just to South America, then we saw that this strong signal of phylogenetic clustering got way weaker, indicating that much of this signal is actually due to some clades being restricted to South America and other clades being restricted to the rest of the Neotropics, which is not really surprising. I mean, we know that those two regions have been separated for a pretty long time. This blue blob is actually really quite exciting because it sort of shows that the method works, because it indicates distantly related palms in an assemblage, and this is very logical in Colombia because there has been spillover across the Isthmus of Panama from this, as a whole, more distantly related palm flora in the northern part of the Neotropics. Well, that indicates that plate tectonics are important for this, but it's still just a small part of the answer to the question why there are different plates in different parts. I'm going to skip this. So, many of you have probably seen this map from Andrew Henderson and Gloria and Rodrigo's extremely useful field guide, where they defined several, I think 7 different palm regions in the Neotropics that are characterized by different, I think mainly based on genera, but different lineages of palms that are restricted to those regions. And we really wanted to know why this is. I mean, we can, for many of those clades, we can build a narrative around why this is, but it can also be analyzed statistically, and that's what we tried at least. And several years ago, I made a new map based on a measure of phylogenetic turnover, which basically measures for two assemblages how similar or dissimilar they are in terms of their phylogenetic composition. So you have high phylogenetic turnover if you have in the one community species from one part of the palm family tree, and then the other one species from another part of the family tree, and you have very low phylogenetic turnover if you have like sister species sitting in one community each. And I used this basically in an ordination and all those small crosses are grid cells in this map. So you can see sort of different regions separating out, and I overlay the 4 palm subfamilies to show that certain regions are dominated by certain subfamilies. For example, there's a coryphoid arrow going in that direction, which is something that you can see reflected in this map, which just shows the first axis of this ordination map out in space. And grid cells that have the same color or similar color harbor a similar, phylogenetically similar palm flora. And there is a certain resemblance, actually a pretty good resemblance. Let me see if I can get back to this, between those palm regions defined in 95 and those areas here. That's not a perfect correspondence, but it is showing up in this analysis. And you can see, for example, this greenish bluish stuff here is sitting in the north, and that's where the coryphoid arrow points, and that corresponds nicely with the coryphoid species, which is the map that I showed some slides ago before. So this is nice. It's sort of kind of, but it's just showing what we knew before. But the big advantage of this is that it can be analyzed statistically. And this is what we did. I didn't actually analyze the ordination axis like they're plotted here. I analyzed the raw phylogenetic turnover and related it to differences in the environment and to spatial distance to see how those things influence the difference in the communities. This is the result, and I've got a reputation for pretty complex figures, and it's not always that easy to understand, so if you want to rest your eyes, look here. It basically just shows that there is if you just look at this upper bar, that there is a fairly large proportion of the variation and significant proportion of the variation of phylogenetic turnover that is determined by spatial distance, indicating that dispersal limitation of clays determines this pattern of different clays being in different areas. This actually increases if I don't just use spatial distance, but I use a measure that also includes dispersal barriers, giving additional support to this idea that this is actually due to dispersal and not just due to some unmeasured environmental factors that might happen to be spatially structured. But then there is also a significant, quite a bit smaller, but significant environmental fraction. So we also find different clades in areas that are environmentally dissimilar, indicating some sort of limited niche evolution. So clades sort of stick to their environmental niche when they diversify. And if you now look down to the rest of the figure, this is basically just broken environment as a whole, broken up into different categories. And the things that show up as significant for the environmental effect are temperature, and interestingly, mainly temperature seasonality, and soil. So this indicates that there is an effect of phylogenetically structured temperature tolerance to temperature seasonality, like it was mentioned in Bastian's talk earlier for the cocosoids. And there is an effect of clades being sort of faithful to their soil, to the soil regime that they belong to. This allows us to, at least in part, answer the question why there are different clades in different regions. But it has to be acknowledged that this is an R-square, and, well, as it is quite typical for macroecological analysis, there is a lot of unexplained variation yet, which might partly be due to the fact that we've been using a gens level phylogeny, and Thomas made a strong point this morning that we might actually be able to get a much better handle on those kinds of things if we manage to get a species level phylogeny of palms. So, functional diversity or morphodiversity. Henrik already showed this map. It's from a review that we published in 2011, showing just the variation of clustering versus solitary palms and palmate versus pinnate palms across a set of 65 community studies in the Americas. And we also looked at different growth forms across habitats and stuff. But regarding continental scale patterns, that's about all we've got. But there are things in the pipeline, obviously. Bastian presented very interesting work earlier today, looking at 3 different clades, 3 different traits across the neotropics, and I'm sure other things will become possible soon with increased knowledge of traits, and so this is really an area in which we have to do some more work. So much for a broad overview of the continental scale pattern. Now I would just like to go a bit into regional scale patterns, and there are really quite many studies in the neotropics. So I'm just going to focus on some studies that I'm comfortable talking about because I've been involved in them, and they're based on the transect data set that Henrik introduced earlier in this talk. This similarity that can be observed for geographically close transects is driven by habitat, which in this case inundated versus non-inundated habitats, which is quite interesting. And we found a similar relationship for our environment, also triangular, also an upper boundary. Things that are communities that are situated in really different environments are always pretty dissimilar, whereas transects in similar environments can be very similar, but they can also be very dissimilar. And where am I now? I'm lost in my here. So we also managed to show that, as expected, the ones that are dissimilar, although they are sitting in rather similar environments, that they are so because they are geographically distant. So environment and spatial distance constraint similarity, habitat matters, soil matters, and region matters. It's basically the take home of this. So that's another one of those rather hard to digest figures. My apologies for that. I just want to show that we also look at the phylogenetic structure of the transect, so whether locally co-occurring species were close relatives versus distant relatives. And we found an overall pattern of positive relatedness. Close relatives tend to co-occur. We found that this differed across habitats. So there were certain habitats for which this was not true, and others where there actually was a tendency of distant relatives to co-occur. And yeah, exactly. Oh, yeah. Yeah. So we also did the same thing that we did for the continental scale. We scaled the species pool, in this case to the habitat, and we found that when we restrict the species pool to the habitat, that much of this clustering effect actually disappears, indicating that diversifying clades are faithful to their habitat, and that close relatives tend to co-occur because they have similar habitat preferences. That was our interpretation of this. But we also found, at a shallower phylogenetic level, we also found a geographic signal indicating that very closely related species also tend to sit in the same geographic area. So taken together, evolution of the habitat niche matters and differs among habitats because we got different amounts of change in different habitats. Oops. And I forgot to put the geographic. Anyway, so what's next? So I don't think we are at the point yet where we should be redoing this review. I guess we should at some point, but not yet. It's just important to remember that the holes in this review, in this figure, don't necessarily reflect that something is not important. It may just as well reflect that it hasn't been studied. And there is still lots to be done. Although, as I said, the neotropics have been the most actively studied part of the world in terms of those things, there's still a lot to be done. You also notice that this is only about distribution, community composition, and diversity. The whole phylogenetic and functional thing is basically missing, which is because at the time when we did this, there was nothing. We have added a little bit now. Other things are in the pipeline. It's actually really exciting to see how much is in the pipeline. And that's definitely something where we need to expand and try to fill the holes. But there's another thing that I think we should be doing. And then just stepping back a little bit from this metricological / community ecological approach of looking at diversity descriptors and spatial units, and taking a slightly different angle where we focus on, in the first place, on individual species. We need to better understand the niches of individual species. For that, we need high-resolution range-wide and very clean distribution data, which is something that is attainable but not easily. The trend sets are really good. Other data sets like GBIF can make a contribution, but we need to work on getting more data. We need to keep assembling trait data, which is being done. There are really exciting things in the pipeline as well. For example, I have a colleague at TU, who unfortunately can't be here, but she's looking at hydraulic traits of palms in relation to species distribution. So that's something that can be really interesting to characterize the niche. High-resolution environmental data, which is one thing that is sort of lagging behind a little bit. That's something I realized when I was working with the transit data. We have really good spatial coverage and resolution there. But for example, if you want to look at climate across the Amazon, world climate, based on a few weather stations, widely spread across the basin, highly interpolated, you don't get any signal from that. And another thing we need is realistic niche models. And by realistic niche models, I mean niche models that have a functional foundation, that are based on traits that can actually be used, in a model, in an evolutionary model of diversification, niche evolution, and dispersal on different time scales, but importantly in deep time. We need a species level phylogeny for that. We need better paleo-environmental data, and we need realistic models of range evolution. And all this together can basically allow us a, I would say complementary approach, complementary to the macroecological approach, to understand palm diversity, where we look at the evolution of ranges, or the evolution of traits underlying ranges, and the dispersal of lineages through time, and basically studying how those distributions that vary over time on a phylogeny come together to form the patterns of species resistance, composition, the patterns of phylogenetic diversity and composition, the patterns of functional diversity and composition that we're so interested in. I think that's one road that we need to take to understand this. So I think I overran. We would like to thank a lot of people who have contributed to this work, and funding was very popular organized and giving us the opportunity to give this keynote. Thank you very much.